In the previous video, we discussed that intermediate band solar cells can tackle the Shockley quasar limit assumption that a solar cell is transparent to photons with an energy below the bandgap energy. We also discussed the strange behavior of quantum dots. Let's now look at how these quantum dots can be used to create an intermediate band. This figure shows the band diagram of a bulk material. We now integrate a quantum dot with a low bandgap energy with respect to the bulk material in the bulk matrix. At the position of the quantum dot, energy states will be present in the bandgap of the bulk material that an electron can occupy. So what happens if we integrate a number of these quantum dots? Let's extend the band diagram of the bulk material and position a second quantum dot near the first one. This quantum dot will also create energy states in the bandgap. If enough quantum dots are integrated in a material, continuous bands of allowed energy states are formed in the bandgap of the bulk material. As a result, the band structure of the semiconductor is effectively changed. The second concept aimed at utilizing sub-bandgap photons is spectral upconversion. The main idea of spectral conversion is to add an additional layer to the solar cell consisting of a material that can alter the incident spectrum. The figure shows two low-energy photons with insufficient energy to generate an electron-hole pair passing through the absorber layer. Spectral upconversion works by combining the energies of these low-energy photons into one higher-energy state, which can then radiate an upconverting photon back into the solar cell active layer. The upconverting layer should be placed at the back of the solar cell to prevent the parasitic absorption of photons with energy above the bandgap energy. Further, placing the upconverting layers at the back prevents them from being irradiated by high-energy photon, which might reduce their lifetime. Two distinct material systems have been employed to produce photon upconversion for solar cells. So-called triplet-triplet annihilation upconverters use organic dyes with rationally ordered energy levels. These upconverters operate at shorter wavelengths between 500 to 800 nanometers. On the other hand, rare earth upconverters, which make use of atomic transitions within lanthanide ions, work in the region around 1500 nanometers. Both approaches have already demonstrated an enhancement of the solar cell efficiency. You now know how intermediate band solar cells and spectral upconversion can tackle the assumption that sub-bandgap photons cannot lead to charge carrier generation. The next assumption of the Shockley quasar limit is that photons with an energy much greater than the bandgap energy can only excite a single electron-hole pair. Spectral downconversion and multi-exciton generation are two concepts that challenge this assumption. The idea of spectral downconversion is to use an additional layer to split one high-energy photon into multiple lower-energy photons. A high-energy photon is absorbed at the front of the solar cell and converted into at least two photons with lower energies. If the energy of the initial photon is more than twice the bandgap energy, both photons can generate an electron-hole pair. This means that the maximum theoretical EQE of 100% at the wavelength of a blue photon can be increased to 200%. If the photon had high enough energy to be split into 3 photons with sufficient energy, a theoretical EQE of 300% could be obtained. In contrast to upconversion, a downconverting layer has to be at the front of the solar cell, as highly energetic photons have a high absorption probability and are therefore quickly absorbed in the absorber layer. Because of the required placement at the front of the cell, parasitic absorption might be a problem in this technology. Just as with other third-generation concepts, quantum dots can be used for spectral downconversion. If quantum dots were to be used for downconversion, an ensemble of nanoparticles would be embedded in a host material in very close proximity to one another. The figure shows two silicon quantum dots and their respective band diagrams. Now, a high-energy photon is absorbed by a quantum dot 1, resulting in an electron being excited high into the conduction band. In contrast to a bulk semiconductor, the excess energy of the photon is not necessarily lost as heat, but can be transferred as a quantized energy package to a neighboring quantum dot. Here, a second electron is excited into the conduction band of the second dot. As a result, two electron-hole pairs have been created out of one photon. If non-radiative recombination mechanisms like Auger recombination and Shockley-Reed-Hall recombination are sufficiently suppressed, the electron-hole pairs in both quantum dots can radiatively recombine such that each of the two emits one reddish photon. As such, one incident bluish photon is converted into two reddish photons, which can be absorbed by a PV material. Another approach is to enhance the charge carrier excitation by a single highly energetic photon is called multi-exciton generation. Like with spectral down conversion, MEG can be realized with quantum dots. Again, a high energy photon excites an electron high into the conduction band of the first quantum dot. But instead of being lost as heat, the excess energy is again transferred to a neighboring dot. In this second particle, another electron is excited into the conduction band. Now, however, the charge carriers of the two excitons are separated and transported to the PV active layers before they can recombine. Therefore, in contrast to spectral down conversion, two or more excitons are generated rather than two lower energy photons. Consequently, one incident photon results in more than one generated electron. The final assumption we will discuss is that any photon above the band gap is lost due to thermal relaxation. Even if more than one electron-hole pair is generated by a single high-energy photon, most photons will not have an exact multiple of the bandgap energy, and therefore thermal relaxation will still occur. Hot carrier solar cells focus on reducing the thermalization energy loss. In hot carrier solar cells, this is attempted by collecting high-energy electron-hole pairs just after light excitation and before they have a chance to relax back to the edges of the electronic bands. The figure shows the band diagram of such a solar cell. On the influence of light, a large number of electron-hole pairs are generated. These curves show the population of electrons in the conduction band and holes in the valence band just after excitation. This distribution is not in thermal equilibrium, as many electrons are excited into a position further up the conduction band and the holes are excited down to lower levels in the valence band. These charge carriers are called hot electrons and holes. It only takes a few picoseconds for the hot charge carriers to relax back to the edges of the electronic bands. The idea of hot carrier cells is to collect the charge carriers as long as they are still hot. Hot carrier cells require selective contacts which only collect electrons above a particular energy level in the conduction band and holes below a certain energy level in the valence band. As such, a large energy can be utilized per excited charge carrier, as indicated by the Q times V. The average energy of the collected charge carriers would therefore exceed the bandgap energy. At the moment, the main challenge is to increase the lifetime of hot charge carriers such that they have time to move from the absorber material to the selective contacts. So these are the third generation concepts that challenge the fundamental assumptions upon which the Shockley-Queisel limit is based. Note that beside the multi-junction and the concentrator approach, none of these concepts have yet resulted in high-efficiency solar cells. These other concepts are still in the fundamental research phase, and it still has to be seen whether these concepts can be realized in real practical photovoltaic devices and modules. I hope to see you again in the next video.